Good day, everybody. Today I want to look at a quick, easy way to find the definite integral of sine squared and cosine squared, at least with convenient limits, which we often call quadrant angles. No antiderivative needed, no calculus needed, really. So first, we should have an idea of what sine and cosine look like. They're 2 pi periodic, and they're essentially translations of each other. Here we've got sine x, cosine x, and if I put it like this, you can see they're the same graph, just sine is cosine shifted pi over 2 to the right. Or you can look at it as cosine is sine shifted pi over 2 to the left. If I look on the interval from 0 to pi over 2, here's the sine in blue, cosine in red. And for any value, say a little to the right, whatever the sign is at that x value, cosine will have that same value, that same amount to the left of pi over 2. So they're symmetric about pi over 4. And of course, they have the same area under the curve. And similarly with sine squared and cosine squared. We know the sum of sine squared and cosine squared is 1 for every value of x. So if I were to add these two up, the sum would always be 1. And the area under each, well, which one would you say is bigger? Of course, they're equal. There's this kind of a symmetry there. So the area under cosine squared is the same as the area under sine squared if you go the full amount from 0 to pi over 2. If you do some other range of x, then the area under sine squared and cosine squared would be different. But from 0 to pi over 2, they're obviously the same. And that just continues. If I look at the graph of cosine squared, sine squared, again, they're just translations of each other. And so with those facts, we can get these results. So for sine squared, if I have quadrant angles like 0 to pi over 2, then I know the integral of sine squared plus cosine squared would be that full length of the interval, pi over 2. So it's the length of the interval. Each of those integrals contributes the same amount. So if they each contribute the same amount and their sum is the length of the interval, then sine squared must have been half, so pi over 4. And similarly with cosine squared, I didn't list it. And that's all there is to it. With cosine squared, again, nice quadrant angles. And by quadrant angles, I mean the angles 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. So those are the quadrant angles, the angles you would get at the x or y axis. So again, if I'm integrating from 0 to 2 pi of cosine squared, the length of the interval is 2 pi, so this will give me pi. And why is that? Because the sum of sine squared plus cosine squared is 1, so that integral would be 2 pi, but each one's going to contribute the same amount. Again, back to the graph, from 0 to pi over 2, they each contribute the same amount. From pi over 2 to pi, they contribute the same amount. From pi to 3 pi over 2, they contribute the same amount. And from 3 pi over 2 to 2 pi, they contribute the same amount. Always like that. So another example, again, just this would be less common for your limits, but pi over 2, 3 pi over 2, those are quadrant angles. The length of the interval is pi, so sine squared will give me half that. Again, because if I integrated sine squared plus cosine squared, I'd get the length of the interval, and each contributes half. So half the length of that interval is the result. You can put any integer here, and the same result holds. And that's because, like, here's cosine of x. If you then do, say, cosine of 2x, you're going to speed it up. So it'll be only pi periodic, but specifically from 0 to pi over 2, if you look at cosine squared, you're going to be contributing the same amount as sine squared. So here's sine squared and cosine squared of 2x. So, and actually from 0 to pi over 4, they contribute the same amount. And then from pi over 4 to pi over 2, they also contribute the same amount. But in particular, from 0 to pi over 2, there would be the same amount of area under the curve. And if I did sine squared of 3x, cosine squared of 3x, now it's going to happen 3 times. So from here to here, which is pi over 6, from here to here, pi over 3, and then from here to here, pi over 2. They each contribute the same amount. And so in particular, from 0 to pi over 2, they each contribute the same amount. And I think we see the pattern by now, but one last time. Sine squared of 4x, cosine squared of 4x. So now it's 1/4 of pi over 2, which would be pi over 8. So from 0 to pi over 8, they contribute the same amount, then to pi over 4, then 3 pi over 8, and then pi over 2. So it happens 4 times that they each contributed the same amount. And in particular, from 0 to pi over 2, they contributed the same amount of area. So again, if my limits are quadrant angles, I know the length of the interval is pi over 2, so this is going to give me half that, pi over 4. Because, again, sine squared of 3x plus cosine squared of 3x is 1, so that integral would be just the length of the interval. And they're each going to contribute the same amount, so they each contribute half of that. Oops, half of this, pi over 2, which will be pi over 4. So again, you really know 2 things. In integral 0 to pi over 2 of cosine squared of 3x would be pi over 4 as well. And well, if you want to get more detailed, as we saw, you can actually go from 0 to pi over 8 if it's cosine squared of 4x, right? So it's just 1 over this number of pi over 2. So 1/4 of pi over 2 is pi over 8. They're each going to contribute the same amount. So technically we know that. And we could even change this, but it's getting harder to do super quickly. Right? So sine squared of pi x, cosine squared of pi x, it actually happens at 1/2. They contribute the same amount. And then up to 1, they do it a second time. So this top line holds no matter what your limits are. Integral from a to b of sine squared plus b cosine squared is always going to be b minus a, the length of the interval. It's only at convenient limits where then they also contribute the same amount, so each contributes half of that length of the interval. All right, so that's the result. You should be able to get integral of sine squared and cosine squared of any integer multiple of x very easily now if the limits are quadrant angles. So hope that's helpful. Thank you, and have a good rest of your day.